This podcast is supported by Hannover Messe, your meeting place for the industrial community.
Hello, everybody, and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber, and today I have two guests, Dr. Martin Bischoff. Hello, Martin.
Hello.
And Dr. Michel Tocic. Hello, Michel.
Hi, Robert.
Both of you work at Siemens. Before we start, please introduce yourself briefly to the listeners. Martin, you can start.
Thank you. So my name is Martin Bischoff. I'm working at Siemens Technology. I'm senior key expert in digital system integration.
Hi, my name is Michel. I'm also working at Siemens Technology since 2014. I have a data science background, did my PhD in the field of reinforcement learning, and I'm also a senior key expert for industrial reinforcement learning and the ecosystem around this topic, deploying it to cloud and so on.
Okay, let's start with our interview. Our topic today is the optimization of a conveyor belt that transport candy bars. I think that's the best episode we ever had because we talk about candy bars and AI. I think it's a good combination to talk about that topic. And when we talk about optimization of a conveyor belt, it doesn't sound like a rocket science at first for me, Martin. Can you please tell us a little bit about the starting point, about the project?
Of course, accelerating a conveyor belt or controlling a conveyor belt itself is not really difficult at all. But looking closer at this particular application, it's a lot more complex because we've got a whole set of conveyor belts, and the task is really we have randomly incoming material that has to be placed in given output slots. And that's really a complex task where the application engineers developing the original application without AI took several years to develop.
They programmed several years on this?
Yes, they did. It's really complex because we've got a lot of conveyor belts. We need to think about using the conveyor belts for buffering in between. We need to place the chocolate bars right in the center of the slot. And the material flow incoming can be random. So it's really a complex task. It's not really about controlling a single conveyor belt and maintaining the speed or such, but it's really making sure the overall production machine works as efficiently as possible. And this includes really placing the material in the predefined slots on the outlet.
And the customer came to you and asked for your help, or what was the situation like?
The original situation actually was like this. Michel and myself, we've been working on combining physical simulations with reinforcement learning already since 2018. We've been together in a project with the Technical University of Munich, and it was not related to industrial production machines at all in the beginning. And then we saw that it's possible, and we basically proposed it to our management to further go into that direction. There's a certain fund for this at Siemens called Siemens Innovation Fund, where we proposed the idea. And so in beginning 2020, Michel and myself, we went to Wittelsbacher Platz and presented exactly this topic to Roland Busch. And we got the initial financiation for that to basically do the first initial demonstrators.
How does the project start then? What were the most important points in this project?
Thinking about the overall workflow, we want to train AI on a physical simulation model. So the key criteria is at first we need a simulation model, of course. We need a coupling between the AI and the physical simulation model. Then we need a training environment for the AI to train on. And once we got a trained AI, we need to bring it onto the machine. That's probably the most crucial task, especially when we focus ourselves on Siemens control units only.
So let's start with the simulation part, because it's very interesting. I think 3 episodes we talked with a startup, and the guy told us before you do a reinforcement learning, you have to be able to simulate your system. How did you do that?
Well, the task basically is to make sure that the AI feels as if it would control the real machine. So the simulation model must produce the same outputs, and AI will give the same inputs as in the real machine, and the simulation model basically has to behave the same. This means for our chocolate bar machine, the AI will have to give set points, velocity set points for the conveyor belts, and it will receive the actual states of the machine. This is all sensor data. There are light barriers in there, for example, and also position signals and velocity signals of the conveyor belts. All such signals are typically available also in conventional controls, and this is provided to the AI. And then AI has to train and develop a control for that.
Michel, you want to add something?
Well, for the simulation of our system, we basically have two options. The first is, if you're lucky, we have an exact physical simulation of the system, which is typically based on a physics engine. And this is what Martin provides to me in our project. But if this is unfortunately not available, we are lucky to have another AI-based option. That is, if archive data from the system is available, we can train a neural simulation model based on the data. And finally, we obtain a data-based state transition model, which is typically represented by a recurrent neural network. At the end, we then train the AI control against one of these two simulations. And the challenge in our case is that we have an environment being controlled at high speed. Think of that we have small control intervals of about 4 milliseconds, where control signals must be provided to the production machine in real time. And our conveyor belts are operating typically at speeds of about 1,000 millimeters per second. And therefore, control signals must be precise for achieving our task goal with high quality. And therefore, we rely on a very exact physical simulation of the machine at training time of our AI controller.
I have one more question, Michel, because you mentioned these two options, the simulation based on a physical system and these neural simulation. Can you go a little bit deeper in this neural network simulation? Where do you see use cases for that?
Oh, yes, I can go a little deeper. And let me tell you a few use cases where I've been involved during my time at Siemens. When I started at Siemens, I was involved in the simulation of the combustion behavior in gas turbines, where a reinforcement learning controller is then trained against such database neural network models subsequently. And where at the end, the controller will actually steer certain valves in the gas turbine. And in the domain, it was a really great success. Another example I have also been involved was the prediction of switching times at traffic light intersections. Imagine that you can predict the switching time, and what you can do with this result is that you can develop a so-called speed advisory that can tell the driver of a car how to ideally adjust speed in order to reach the green wave. Another example I've been working in was the prediction of emissions at measurement stations in cities, emissions such as particulate matter or nitrogen dioxide. And what we've done was that we predicted the next 100 hours in order that the cities can act based on this forecast, for example, by doing some mitigation measures. And what all those examples have in common is that you need to deal with those long time horizons. The neural network requires a precise state signal at the current point of time. And from this precise state signal, it should predict the successor state or even 100 successor states as with the emissions with high quality. And such state transition model is yet then, as I already told, used for developing or training the reinforcement learning controller. And in order to deal with so many time steps required for building up our state signal, we typically use specialized neural network architectures. For example, there's a well-known long short-term memory model developed by Sepp Hochreiter and Jürgen Schmidhuber.
What is better, to have a physical simulation or to have this neural simulation?
Definitely the physical simulation.
Yes, sure.
No question.
Say so. The answer is it depends. It really depends
yeah.
on the application. If the system is very well understood, if we like for the chocolate bar machine, for example, we know what drives are in there, the friction of the conveyor belts and every detail of the machine, it's so natural to directly code this into a physical simulation model because all parameters are there. If it's more complex and there are several unknowns that we cannot clearly measure, it makes a lot of sense to just collect the data, like the inputs out and outputs of a black box, and then train an AI to reproduce the interior of the black box.
Okay, well, this brings us into a new direction of research, which is called physically informed neural networks, that can embed the knowledge of physical laws that govern a data set in the learning process and can be described typically by partial differential equations. And those equations have parameters such as the length or the weight of a pole, which are measurable, but the equations in practice require also other parameters which are not so easy measurable, for example, friction. And the estimation of those parameters is left to the neural network part, being trained by the observed data measurements from our physical system. And the output of the neural network then becomes the input to the physical equations, and the reinforcement learning controller with high quality data and states you have not visited before.
But is it possible to combine it in a way?
Yes, definitely. That's what I really wanted to say next. It depends really on the actual application, and often the best possible compromise is really to combine both worlds, like the data-based model and the physical model. And for example, if frictions are unknown, just let the AI learn this particular component of the system, whereas other components which are well known can be modeled physically, and then let the different models interact with each other.
Okay, we have this physical model, we have the simulation. How do you train the AI? What was your feedback channel for the reinforcement learning?
Yeah. In our chocolate bar application, the feedback channel was very easy to describe. The goal is to place the product on the outlet conveyor belt within a certain position, so that the plastic bag packaging machine, that machine works in fixed time intervals, receives the chocolate bar at the right point of time. And in this way, placing the chocolate bar at the correct position on the last conveyor belt yields the highest possible reward to our reinforcement learning algorithm. And in turn, the more distant the chocolate bar was placed, the lower our reward signal becomes.
So you go on the end of the process and then you go all steps to the start.
Yes. And this also highlights again the problem of long time horizons for building up an appropriate state for the neural network just mentioned before. And in order to answer your question, we may support learning by adding additional intermediate feedbacks, for example. In the chocolate conveyor belt system, we also reward near identical conveyor speeds when a chocolate bar transitions from one conveyor to the next. And in this way, we are able to ease a bit the problem of modeling friction, right? And this can be seen as a sub-goal, which should be weighted not too much, but yeah, at least a little bit.
And you train this AI model in the simulation, right?
Yes. And in our case, the AI plays with the simulation. The AI tries out random actions and observes the consequences of them. And in this way, it finds out whether they are helpful or not. And at the end, our reinforcement learning controller is just a simple feed-forward neural network whose weights are optimized by the RL algorithm. And in our case, the reinforcement learning training process requires roughly 3 to 4 hours of training time, during which the AI plays in parallel with multiple instances of the physical simulation of the conveyor belt system.
When we talk to our listeners at events or at trade fair shows, this topic reinforcement learning is always a little bit of magic, you know? And can you explain a little bit what happens in the neural network when you do this training?
Well, when you train a neural network, this typically requires an error signal used for optimizing the weight matrices towards lowering that error signal. In our case, This is the difference between the observed and the expected cumulative reward over time. And in this way, then we train a neural network, which is called a value function network, that generates the expected cumulative reward signal, which then is compared to what we observed from the simulation. And the arrow between both signals then is used for adjusting the weights of the actor network. This is the first one I've told you, that provides our control signal for the conveyor belts.
We do not talk about big data or smart data. We talk about, for a lot of people in the industry, a totally new approach. How you explain it to your customers? Because I think a lot of customers also don't know what is happening then there.
One nice way to explain what's happening relating to existing methods is basically that a neural network can be understood as a kind of model order reduction, where the weights in the neural network or the neural network itself tries to reproduce something optimally, as Michel just said, but the calculation effort to calculate that and the mathematical operations that happen there and space, storage space and options are very limited. So it's really trying to compress, for example, in our case, an optimized control for a certain machine in a kind of minimalistic system. It's like a model order reduction, and that's very helpful, especially when it comes to fast calculations, for example, if we want to have the next set points in a short amount of time, for example, also for complex tasks.
Where did you train the AI? Is it a cloud infrastructure? Is it an edge infrastructure, or directly, I don't know, on a PLC? Where is this training happening?
The training is happening in the cloud. So this is our goal because we want to build scalable products. But inference of the models is very, very close to the machine on the PLC, programmable logic controller, close to the conveyor belts.
Mm-hmm. When we have episodes about reinforcement learning or other topics, the first question of our listeners is, how does the model get to the controller? How do you transport it and integrate it in my machine? I think that's, for the most listeners, the most important part of a project, because it's fine to have this simulation and yes, it works and it's fine and we have this proof of concept, but how does the model get to the controller?
Well, because our model is a simple multi-layer perceptron containing a few weight matrices, deployment becomes relatively easy. In fixed time intervals, the vector of machine data from several past time steps simply becomes multiplied by the neural network's first weight matrix, and this generates a vector called the hidden activation. And this vector again is multiplied by another weight matrix, and out of the process, then we derive our control signals. And to describe mathematical operations for inference with the controller model, they can run in real time on a programmable logic controller in less than 1 millisecond.
Okay. Martin, you want to add something?
Yeah, and in terms of actual deployment, there's a Siemens product called OpenTip Development Kit, and with this external software can be integrated into Siemens TIA portal. And so all we had to do was bring this trained neural network from Python into TIA portal. And the nice thing is then that it can be integrated into an existing automation application and is they're represented as a common function block, like the conventional control itself. And when it comes to checking and making sure that the AI performs within limits, one can adjust and add some additional function blocks to verify that.
It's interesting because you mentioned this customer and his candy bars. I assume that there are Siemens controllers, Siemens drives. How difficult is it to transfer your approach to other applications with, for example, a back-off PLC or, I don't know, an ABB drive or whatever?
Like reinforcement learning is applicable to like any control in the end.
So it's no problem to transfer this approach.
No. Imagine that the chocolate bar application, this is not our first reinforcement learning application, and we learned a lot in the past from totally different applications. And in the chocolate bar application, we applied our knowledge and refined it a little bit to this particular kind of learning problem. Do this, and it works perfectly.
Do you sell this specific model to other customers? Is it an add-on, or do you name a function block, or do you sell this model?
We don't sell it yet. We got the first demonstrators running by end of last year or so. And now we are trying this out together with selected customers in a co-creation phase. But we are going to offer this as a solution business in the future and maybe also as a product.
Because you mentioned the customer, what does the customer need for your reinforcement approach? What is important?
Well, essentially, the customer needs to have at minimum a good data scientist or engineer that configures the neural network model, as well as a training and inference stack around it. And you also need someone that provides the physical simulation, such as Martin in my case. And if not available, you can survive when you at least have some observed data from the physical system for training a neural simulation model. This is the second point I mentioned before. Once you have the simulation, then you can start training the controller network.
Actually, the chocolate bar machine is understood. We call that Intelligent Infeed, what's happening there to place any material in predefined slots on the outlet belt. And now we set up a training environment for that, and we know how we can deploy this particular neural network onto a Siemens PLC. And so it's relatively easy to transfer this from one application to the other. All what needs to be done is adjusting the parameters, retraining, and deploying it again. When it comes to new applications, and with our co-creation partners, we also try out various other applications.
For example?
For example, unreeling. That's one interesting thing that we try out at the moment, where we have a film reel that's being unreeled. It's also a very huge market in industry. And it's also a very similar concept where we have got randomly incoming material, which needs to be packed as efficiently as possible. And that's where also AI comes to play. And in all those methods, once we understood the application and we set up the training environment and we got the workflow, we can easily adjust it to other applications. And we basically need the data science and our experience and know-how in the beginning. And once we got it established, we can easily adjust it by configurations as such. So in the end, our customers would have to deliver a certain their particular machine configuration, their application, and then their particular solution can be trained.
Michel, you want to add something?
It is important to have a data scientist that has a good intuition about what the AI model requires. For example, in terms of feature processing. Think of raw data is most often not sufficient for an efficient training of an AI in short time. And constructing artificial features that can be derived from the raw machine data, this really helps in reducing a lot of training time and in consequence also money in terms of costs for the training. In the chocolate bar application, we process the raw sensor signals from the light barriers in a way that we construct a sawtooth function. This goes over time, over many time steps. And it responds to rising and falling edges for each of those binary sensor signals. And in this way, we transport the information about when the state switching took place in the past over many time steps into the future. And I adopted this idea from another totally different project with Siemens Mobility, which is now Unix. This is from the traffic light prediction project, where we predicted the signal switching behavior of the traffic lights. And such kinds of feature engineering is what the application engineer without AI background typically does not know. And this is where we have this great work together with the data scientists and the application engineer.
I want to come back to this fantastic candy bar example. What will happen when there's a new candy bar? How can you adapt then the model on a new candy bar?
So there are different options. One is if we already know that we've got a set of candy bars available, we can train AI with respect to these different options, such that immediately when it changes, it directly knows what's going on and can perform accordingly. If this is a new thing that we haven't thought about during training before, we have to retrain normally. And like the nice thing is, it's basically similar to a conventional control. Whenever something changes on the machine which hasn't been foreseen, the code needs to be adjusted. The nice thing is that it's standardized with the AI how to retrain, and we know that the solution will be there in, let's say, 1 or 2 days, depending on the training effort. Whereas with conventional control, we need the corresponding application engineers who know about this application to be there, who dig into the code again and make the right changes. And then they need the whole testing again. And all this can be like processed faster in an automated and standardized way with AI.
Okay. Michel, you want to add something?
Yeah, the important part in our case is that we are not performing online learning on the machine simply because it's too dangerous.
Because of security, or what means dangerous?
Well, when you perform online learning, this implies that you must do some trade-off between exploration and exploitation, right? This means you occasionally need to try out random actions or control concepts, and you learn the consequences of them. But when you do exploration on conveyor belt systems running with speeds of 1,000 millimeters per second, believe me, this is not a good idea. And in consequence, our AI can only deal with those or similar situations as it has seen from the simulation during the training process. But please keep in mind that the AI model also has some generalization abilities up to a certain degree, which is useful for dealing with similar and not seen situations during training time. This is our backup. And after training, the weight matrices of our model simply become freezed for safety reasons, and the weights do not change anymore. And you can evaluate the controller in arbitrary situations and see how it would respond. And if you then have a good result and a reliable result, then you just deploy to the machine.
Martin?
Yes, concerning online learning, there are many reasons why some machine builder or some OEM wouldn't want to have that in his production facility. Like one thing, AI will try out anything, and that's the dangerous thing that Michel talked about. And this might damage the machine, this might cause the production to fail, and many things. The other disadvantage is, of course, that we have not standardized conditions. Like there are many disturbances from anywhere outside that the AI will also consider during training. And additionally, it's bound to real time. We've only got those machines available that we have in terms of parallelization. Whereas in simulation, everything is standardized. We can parallelize things. We can perform faster than real time. And so it cannot be done without.
Mm-hmm. So I need to call you guys when I want to retrain the model.
No.
Currently, yes.
Currently, yes. In the future, no.
No?
Yes, exactly.
Okay, let's talk a little bit about the future of control algorithms. Will reinforcement learning change them totally, Martin?
Yes, from my perspective, yes. The important thing is that application engineers needn't be afraid at all. The opposite is the case. Actually, their work will become more effective, more efficient. They will get new tools. They will be able to provide better solutions. They will need to provide more different controls for better adjusted machines. So basically, new, better tools always augment the existing work and make it more efficient. One could also consider AI as another possibility to just test things in the beginning to see what the computer will do with that problem and better learn from that, from the trained results, and conventional control based on the strategy identified by the AI, for example. Like there are many different possibilities how to incorporate that into application development in the future, but it will definitely change. AI will also play an important role for that.
Mm-hmm. Okay. Michel, you want to add something?
Well, Martin summarized the points very nicely. We can see the transformation of companies already on the market, for example, by acquisitions of small startup companies for lots of money. And they have in common that they have a big focus on reinforcement learning. This is namely DeepMind, which was acquired by Google in 2014, or more recently InstaDeep, which has been acquired by BioNTech.
Is it possible to see maybe in 2 or 3 or 5 years a POC where a reinforcement learning model is included and the user really don't know about that?
Oh, good question, Robert. I think this depends on where the reinforcement learning is used in the PLC. Yeah? Is it used for the actual control logic or for something internally? In general, every control function, being PLC internally or external on the machine, is a potential source where reinforcement learning can come into play. And this is what I tell to our customers, typically when they ask, where can I exchange some function by reinforcement learning? And the answer, which I'm telling them all the time, is that wherever you have, for example, a hand-tuned PID controller, then this is the potential source where you could increase controller quality by exchanging it to a trained reinforcement learning model.
Martin, you want to add something?
Yes, we also touched legal aspects here and things like if it's really feasible that we provide automation applications that have been developed by AI only. But on the other hand, who is really aware on how conventional controls perform in detail? What's done there and what's happening there? Currently, the users, like the OEMs who operate the machine, are not aware what's happening there in detail. And they might actually not, in 5 or 10 years, they might not be interested whether an AI will be operating the machine or this particular feature of the machine, or whether it's been conventional coded. They might not even care because all they need to care about is that it's efficient and safe.
I want to come back at the end to the candy bar and I want to hear some results of the project. Can you give us some numbers?
Yes, the highest benefit is really engineering effort. So as I mentioned in the beginning, originally the engineers took many years for developing the conventional control. Michel and myself, we were absolute newbies in this field with conveyor belt control for intelligent infeed and everything. But Michel managed to model this problem in a training environment very efficiently. And so it was only a matter of 3 months or so to get the training environment working and to get AI trained to solve that problem. So the highest benefit is really engineering effort, especially now that we know how to set up the training environment. It's possible to adjust it easily to other intelligent infeed applications as we are currently exercising with co-creation partners. And so that's the highest benefit. And of course, we also have other benefits when it comes to production flexibility. We've got the possibility to adjust a control now easily in a matter of days, whereas before it was a matter of months to adjust certain parameters. And also when it comes to efficiency, I'm very optimistic that there will also be a set of applications where AI together with conventional control will perform superior than just conventional control by itself, just because we've got new tools. We don't do magic with our neural network. It's just common, simple calculations, what's happening there. So it can be reproduced by manual programming this. But effectively, we are faster. And based on that concept, we are faster with AI. And with that concept, we will be able to explore the solution space more efficiently and find better solutions.
Thanks a lot, Martin. And thanks a lot, Michel, for your reinforcement learning approach of the conveyor belt to transport candy bars. Thank you very much.
Thank you.
Thank you, Robert.